All right, hi everyone. Today we're going to be going over Chapter 8, which covers bivariate correlational research. So we're about at the halfway, we'll just pass the halfway point now. So the chapter is going to get a little bit more specific, and you're going to see some old ideas come back into play, and we'll kind of expand on stuff we've already learned. So throughout the chapter, I'm going to try to reference like where this old material, what chapters that's from. If you are confused about something I'm saying that we've already gone over, it's really important that you take the time and go back to previous chapters and make sure you really understand those concepts before moving on too far. So we're going to see from this chapter on out, the material is really going to start to build on itself. Okay, so chapter 8 is going to go over, like I said, bivariate correlations, and then figure out how to interrogate association claims. And a lot of that stuff is going to be review, but again, we're just going to kind of expand on material we've already covered. Okay, so first of all, what is a bivariate correlation? So a bivariate correlation is an association claim that has exactly two variables. So we've already talked about the different types of claims, right? Frequency, association, and a causal claim. So association claims that have two variables that you're looking at is considered bivariate correlation. Okay, so we've already gone over examples of these. And studies that are looking at association claims, remember, are looking at measured variables. Okay, so you're either measuring something, you can have like a survey or self-measure, you can have some sort of physiological measure, you can have a behavioral measure. So we've already talked about all the different types of measures you can have, but association claims are going to have two measured variables. Okay, and when we're doing a study, if we want to look at associations, the study that we're doing doesn't necessarily only have to have two things that we're measuring. Okay, the study can measure 10 things if it really wants to, but when looking at the correlation, we're only going to be looking at two measured variables at a time, and seeing how they influence each other. So an example we've talked about before, looking at person's self-report score on a well-being scale, so how depressed or happy or whatever they are, right? Rating themselves. And then this study looked at the percentage of conversations that are rated as deep talk. Okay, so this was an observational measure. We talked about this previously as well, but the participants were hooked up to microphones, and what they said throughout the day was recorded, and then their recordings were analyzed, and certain types of conversations were considered deep talk, other conversations were not. Right, so here we're comparing two measured variables, a self-report measure on well-being and an observational measure on how often they have deep talk in the day, right? So that's one example. Here's two other examples. You can have a marital satisfaction. So this was a self-report measure where you met your spouse. They answered a survey or questionnaire, online or offline. And then they gave some sort of marital satisfaction rating, which would also be a self-report on some sort of scale or whatever it may be, right? So it's trying to compare where they met the spouse and how happy they were. I'm sure the survey had more than just two questions. It probably had additional questions about, whatever, deep talk, time spent together, maybe financial information, maybe gender information, right? So there can be multiple things that the study's measuring, but this correlation, again, is only looking at two variables. And then another example, we've talked about this already as well, but looking at the frequency of multitasking and the ability of multitasking. So they had a questionnaire asking how frequently they multitasked, and then they did a multitasking test, and behavioral results were measured at how well they performed that task, right? And then these two variables were correlated against each other. Okay, so anytime it's bivariate correlational research, it's an association claim. with two measured variables. Association claims, again, always going to be measured variables. Okay, and if you look at the examples we gave, some of them have two quantitative variables. Remember, there's different types of quantitative variables: ratio, interval, ordinal, scales. But quantitative, remember, is numbers. So you can either have an association with two number scales, or you can have associations that have some sort of categorical data. So for example, this one here, offline or online, that's not a numerical number, right? That's categorical. They're either in the online or offline category. Okay, so depending on what the variables are, what type of variables we have, there's different ways that we're going to analyze the results. Okay, so let's start with two quantitative variables, two numbers. We've already kind of talked about this as well. This is hopefully a little bit repetitive for you guys. I'm going to kind of breeze through it. But if we have two quantitative variables, so here's the percentage of deep talk measured, up to 100% of conversations, and then the well-being scores that there's, answer to some sort of questionnaire, two numbers compared against each other. You're always going to have your results presented as a scatter plot for this. Okay, so each individual person, their two variables are going to be plotted against each other. So this person, their well-being scale was around -2, and they had about 0% deep talk. So not very happy, not very much deep talk in their marriage. Let's see, this person, well-being score was 1, so higher, and they had about 60% deep talk. Right, so all of these individual points are individual people with their individual data points. You put them on a scatter plot, and then we can look at the R value or the correlation coefficient to see the strength of this relationship, the strength of the association. Okay, this example, the R value is 0.28. We already talked about R values, right? The closer to 1, the better. It could either be +1 if it's a positive association. If it's a negative association, -1 works as well. And then closer to 0 is a weak association. So we didn't introduce this previously, but now we're going to add it on. So the R value, how can we tell if it's, a good association or not? We talked just generally, but now we have some actual guidelines. So Cohen's guidelines to see, if the strength of the association is good or not. So if you have an R value of approximately 0.1 or like below, that's a small or weak effect size. Okay, 0.3 or -0.3 is medium or moderate. And then 0.5 or above is going to be considered large or strong. So this just gives you sort of benchmarks to figure out if your association is weak, medium, or strong. Okay, so hopefully that mostly is just review for you guys. Here's just another example looking at that multitasking. So we have the multitasking score, and then the self-report, the frequency of multitasking. So you can see again the scatter plot, each individual point is a person and their results. Here the R value is -0.19. So you can see there's kind of like a little negative trend here. Up here seems to be higher, kind of down here. So there's a negative association, we have a negative R value. So as we increase one variable, the other variable is going to decrease. But this is not a very strong association. It's small. What's M stand for? I don't know why it says, oh, small. It's close to maybe being moderate, medium. I'd say this is a small association though. Okay. So anytime you have two quantitative variables, you're going to look at your results with a scatter plot and look at the R value and those Cohen's guidelines to figure out the strength of your association. Okay. If we have some sort of categorical data, what we're going to do with that data is going to be different. Okay. So if we have categorical data, only one of the variables typically is going to be categorical. The other is going to be quantitative. So we're going to see how we can graph those and then analyze to figure out, if the results are meaningful or significant or not. Okay, and remember, again, I'm going to say this over and over and over. For a correlational study, both variables have to be measured. Okay. Once we start manipulating variables, that is going to lead us into some causal causal claims, not association claims. Okay, so two measured variables always. We're not manipulating anything in this chapter. All right, so if we have a categorical data, how do we graph that? So we could do a scatter plot. So look at this has the marital satisfaction, right, and where you met your spouse. So you could definitely do a scatter plot. Because we have categorical data here, though, it's not really easy to figure out like what this means. There might be like a little trend going this way through these, but it's really not telling us too much. And we do this because we only have, categories down here. The R value is not really going to tell us anything that we need to know. Okay, so scatter plot we can do, but it is a lot better to graph association claims with causal or categorical variables as a bar graph. Okay, so instead of plotting the individual points, we're going to take the mean, which hopefully you guys know what a mean is, but taking the average. So everyone who met their spouse online, take their marital satisfaction, add them together, divided by the total number of points to get the average marital satisfaction for online compared to offline. Okay, so this gives us a better, prediction of marital satisfaction for each of the categories or each of the groups. Okay, so with categorical data, again, scatter plot could work, but typically you're going to do a bar graph and graph the means for each of the categories. Okay. So obviously for the scatter plot, we use the R value to determine, if it's how strong the association is. We can't do that with a bar graph. So how we analyze is by using a t-test. And a t-test is just a statistical test that tests the difference between the two groups' averages. Okay, so seeing if the averages, the means, are statistically different from one another. And this is not a statistics class, so we're not really going to get into how to do this too much. As long as you know for categorical data and bar graphs, we're going to use a t-test to determine the statistical significance between the means. Okay. What makes a study correlational? Again, I've said this 3 times already, 4 times already. But remember, we need 2 measured variables to make a study correlational. Okay, if we're manipulating variables, we're going into causal claim territory. Correlational, another word is association claim. We have to measure both of our variables. Okay, and remember, we can graph with a scatter plot or a bar graph and use a R or T test to determine the statistical significance, right? All right, moving on to the second part of this chapter, how to interrogate association claims. So some of this is review, but when interrogating association or correlational claims, there's some different things we're going to have to look at. To look at construct validity, again, this hopefully is review, but how well each variable is measured. Statistical validity, how well does the data support the conclusion? So look at the different R, T values, P values, which we'll talk about in a minute. Internal validity, can we make a causal inference from the association? So internal validity we don't need for association claims, but it's good to keep it in mind to kind of make sure that it's not actually a causal claim. Okay, be able to explain why we don't have causation. And then the last is external validity, seeing if we can generalize the association to. Which groups of the population or samples of the population can we actually generalize our association to? Okay, so I'm going to go through all of these, and there's going to be, I'm going to expand on all of this stuff as well. So let's start with construct validity. This is all just review, and same as frequency claims. looking at the construct validity, though, of each variable. Okay, so for frequency claims, you have one variable that's measured. Association claims, you're going to have two measured variables. So for each of those variables, you need to make sure that you have a good construct validity. Okay, so how well was each of these variables measured? Is the measure reliable? So every time we do that measure, is it consistent? Is it consistent between the people who are doing the measuring? So if you're measuring, looking at the amount of deep talk people have in a day, people who are analyzing those tapes, do they have the same, um, you know, not same categories or a way to define what is deep talk, right? So if the two people listen to the same tape, would they get the same amount of deep talk? If you had people take a survey, if where they met their spouse, are they going to answer online and offline every time? Test retest reliability. Okay, so is this measure reliable? And then also we need to make sure that the measure is valid. Okay, so is it measuring what's intended to measure? Criterion validity. What about face validity, concurrent validity, discriminant and convergent validity? All those things we talked about in chapter 5. You should know what all of these mean, hopefully by now. And for association claims, everything we already talked about is the same. You just have to do it for both variables. Okay, so if we're looking at deep talk and well-being, making sure that we have reliable measures. Every time we measure deep talk, every time we measure well-being, we get the same results. And making sure that what we're measuring, our questionnaire for your well-being, is it actually measure your well-being, or maybe it's measuring something else. Okay, so making sure that each variable has good construct validity. Next, let's talk about some statistical validity. And this has a lot of new terms that we're going to go into here. So statistical validity for an association claim, we need to consider the effect size, the statistical significance of the relationship, if there's any outliers that could be affecting your association, restriction of range, and any possibility of a curvilinear relationship. Okay, which I'll go into detail of all of these. So starting with the first one here, which is effect size, which we've already talked about. The effect size is just the strength of the association. Okay, so again, looking at that R value, the stronger the R value, the stronger the effect size. It's just kind of an interchangeable term. So this graph here would definitely have a stronger R value. Our scatter plot, the points are grouped better compared to this guy over here. So the stronger R value, the stronger the effect size. Okay. And again, we can look at the Cohen's guidelines for determining what the strength of our effect size is. The stronger effect size, the stronger the correlation, again, we've talked about this in previous chapters, means more accurate predictions. Okay, so a lot of times when we're looking at associations or correlations, it helps us to figure out and kind of predict what's going to happen in future. So this example is trying to predict your child's adult height and seeing what's a better predictor of that, their height when they're at age 2 or their mother's height. Okay, so you can see this first graphed the child's height at age 2 against the child's height at 18 years old. And you can see we have a really strong effect size here, very strong association, nice grouping of those data points. And if you look at this one with a mother's height graphed compared to the son's adult height at age 18, we still have some effect size, but it's not as strong, right? We have a positive association, positive relationship, but it's not necessarily as strong. The effect size is not as strong as this first one. Okay, so this first one will be a better predictor of children's height. So if the red dots are all of the actual data points that you graphed where you knew their height at age 2, you knew their height at 18 years old. If you knew a kid's height at age 2, let's say Hugo at age 2 is 170 centimeters, you can put his point into this graph, even if he's still 2 years old, and predict how tall he is going to be, around 172 centimeters, based on your results here, right? Because you have this prediction line. You could do the same thing over here. At 2 years old, Hugo is 170 centimeters. Hugo's mom is 163 centimeters. You could predict his height, 174 centimeters. It's still going to be a kind of close prediction, but not as accurate as this one with a stronger effect size. Okay, so stronger correlations, stronger effect size means more accurate predictions. Okay, this is a lot of text, but I want to just so you guys can read through it. When everything else is equal, a larger effect size is more important than a small one. Okay, so a larger effect size, a stronger effect size is obviously going to be better at predicting, more, reliable, significant data. But sometimes small effect sizes are still really, really important and still very meaningful. So an example the book gives, a medical study on heart attacks and taking aspirin. A small R value was found, 0.03, so it's tiny, the effect size of how aspirin helps with heart attacks. But that effect size is still extremely important because of the number of lives saved. So even though if you were to look at this, you'd say that is insignificant, not important, that small of an effect size still can be significant because it has a huge impact. Okay, so there's 22,000 participants in the study. Half of them are in the aspirin group, half in placebo group. And there are 85 fewer heart attacks in the aspirin group, which, in the big scheme of the study isn't really big. Your effect size is really small. But if it's saving anybody's life, then it's going to be a very important finding. Okay, so they actually stopped the study partway through and gave everyone in the study the aspirin, because it clearly was beneficial in preventing heart attacks. And even if it prevented one heart attack, in medical research like this, obviously you want to help as many people as possible. Okay, good. So the next statistical thing we need to look at is if the results are statistically significant. Okay, so this is going to be a lot of text on the next few slides, but I want to make sure I have it all. So if you want to pause and take notes, feel free. But statistical significance, the definition, so it's referring to the conclusion researchers make regarding how probable it is that they would get the correlation of that size by chance, assuming that there is not a correlation in the real world. Okay, so I'll explain it more in the next slides. But for statistically significant, we're looking at a p-value. We want the p-value to be as small as possible. We want our results to be statistically significant. So a p-value of less than 0.05 is good. Okay, so the next few slides we'll go over the logic. What does the statistically significant result mean? What does it mean if it's not significant? And then effect size, sample size, and how that affects significance. Okay, so this slide I think explains statistical significance a little bit better. I'll read through it, but if you're confused, just read through it a couple of times because it's kind of wordy, but there's really no good way to explain this, right? So researchers are collecting data from a sample and make inferences to the population, right? We talked about the chips in the bag. You're not eating the whole bag, you're eating a sample of the bag, okay? Typically, what happens in the sample mirrors what's happening in the population, given that you have a random sample, right? But that's not always the case. Okay, so if there's an association between the two variables in the population, you're usually going to see an association in the sample. So if you see the chips are salty, your sample of chips are also going to be salty. If there's no association in the two variables in the population, there's probably no association in the sample as well. So if your chips are not salty, your sample is probably not going to be salty. Okay, but even if there isn't an association in the population, so the chips aren't salty as a whole, the whole bag's not salty, there could be a chance that there may be an association in the sample. You might get the one chip that was salty. Somehow a single chip in the bag was salty and that just happened by chance, but it doesn't necessarily reflect the whole population. Okay, so there could be by chance an association in your sample, even though there's no association in the entire population. Okay, so statistical significance is helping to evaluate that the probability of the result came from a population where the association is 0. So it's making sure that the association isn't just random, didn't happen by chance, but there's actually an association in the relationship in the population as well. Okay, hopefully I explained that pretty well, but moving on to more text. So what does it mean if we have statistically significant results? So if we have a p-value that's less than 5%, 0.05 or less, that means that there is less of a chance that the association in the sample came from a population with an association of 0. So it's very unlikely that the result came from a 0 association. Okay, so we want a small p-value because we don't want our association and our sample to be there just because of chance and not show that there's actually an association in the whole population. Okay. If we have a non-significant result, so if it's greater than 0.05, the p-value, it means our result is not significant, not statistically significant, which means we can't rule out the possibility that the result came from a 0 association population. Okay, so if our p-value is high, that means that there's a chance, a pretty good chance, that even though we see an association in our sample, there's not an association in the whole population. Okay, so it just happened by chance that all of our sample had an association when the population, in fact, really doesn't. Okay, so that's not good, right? We want our sample to reflect what's actually happening in the population. So we want statistically significant or a p-value of less than 0.05, 5% results, okay? Hopefully this makes sense. Let's see, effect size, sample size, and significance. So typically, the stronger the correlation, the larger the effect size, the more likely that the correlation is statistically significant. Okay, so the larger the effect size, the stronger the correlation we have. Typically, that means that there's less of a chance that, there's not an association in the population, right? If we have a small effect size, just a sort of an association, but not really, there's more likely of a chance that there's not actually an association in the population. Okay, but we always need to examine the p-value. And the p-value, again, we're not in a statistics class here, but is going to depend on the effect size and the sample size. Okay, so if we have a small effect, so a R value that's small, it still could be statistically significant if we have a large sample. So if we sampled a whole bunch of people, even if the R value is small, it might still be statistically significant. It's less likely for a small R value, a small effect size, to be significant in a small sample. Okay, and again, a large effect size is more likely to be statistically significant. This is because small samples are more easily influenced by chance than large samples. Okay. So here we have just an example of what a paper would look like. You're going to talk about this more in lab, interpreting results of papers. But this is just looking at the different R values, P values. If the P value is less than 0.05, it's going to have an asterisk by it, right? So those would be statistically significant results. P value less than 0.01 would be like super statistically significant, which would be the double asterisk. That's just how you interpret some of the results. Okay, and there's a video embedded in here that I'm not going to play, but it's just explaining what, how to find statistical significance and different statistical t-value, p-value, how to figure all those out. I'll post it on Educat just so you guys have access to it if you want to watch that to kind of get a little bit more of an explanation. If you just YouTube it, it'll help definitely find some stuff. Skip that, hopefully. Okay. One thing we need to take into consideration when looking at an association is the effect of outliers. Okay, so outliers are an extreme score, or perhaps a few, more than one, that lies away from the rest of the scores. Okay, so this can severely affect the associations that we see, especially on the statistical side, and it's going to be most influential when the sample is small. Okay, and it's going to affect your effect size. So, for example, this is a large sample size. Here's a small sample size. Okay, so we can see all the samples are the same, except up top we're going to have an outlier in both of these. So in the large sample, our R value here would be 0.26. If we add one single outlier up top here, our R value jumps to 0.37. So we have a stronger effect size when maybe there shouldn't necessarily be that strong of an effect size. See what I'm saying? In a small sample, the same thing you can see. Our R value here is 0.15, which is very low. And that one single outlier gets us almost to a 0.5, which is a strong effect size. Okay, so R values are always going, or not R values, outliers are always going to affect our effect size, but more so in a small sample than a large sample, right? A large sample has all these other points that are having an influence on the effect size. When we have fewer points, each point makes up, more of that effect size. Okay, so just keep an eye out for outliers. Next thing I want to talk about when it comes to statistics is what's called restriction of range. And this happens when there's not a full range of scores for one of the variables in an association correlational study. Okay, it can make the correlation appear smaller than it really is. So this example is comparing your SAT score to your college grades. And obviously, some schools have a minimum ACT or SAT score they need for admission. So if they're comparing their students' SAT score upon admission to how well they're doing in college, you can see there's some sort of effect size here. There's a correlation. However, we don't see the full picture, right? Because they didn't admit everyone to the college that had lower than 1200 SAT score. So we don't know for sure the correlation between SAT score and college grades because we are missing part of the information. Okay, so this graph down here would show a better example without the restriction of range. Again, the school only admits students from 1200 up, so you don't see the full picture. Down here you can. So this top graph has an R value of 0.33. So there is a correlation between how well students did on the ACT or SAT score and their GPA in college. But if you look at this bottom graph where I have all of the data points, we can see we have a stronger effect size because we have more data and we see the full range. Okay, so it's really important when we're looking and analyzing data that we make sure that we're not restricting the range because obviously it's going to have a big effect on our effect size. And the last thing on this section I want to talk about is something called a curvilinear association. We've talked about, studies that have a positive association, negative association, or zero association. But sometimes if our correlation coefficient is 0, we have no effect size, close to 0, we could have what is called a curvilinear association, which isn't just a straight line as one variable increases, the other increases, or the one increases, one decreases. A curvilinear association, you're not going to see, really the extent of it with just looking at an R value. Because it's not a straight line. So this example gives age in years and the use of the healthcare system. Obviously, when people are young, babies, they have shots, they have whatever, lots of medical checkups, yada, yada, yada. As you get older, your use of healthcare is going to decrease because you're not getting shots as much, you're not whatever, you're not doing that much, hopefully, in the hospital or healthcare in general. And as you get older, your use of the healthcare is going to increase as well. Because as you get older, typically people get ill, have to get checkups more frequently, have to get mammograms, colonoscopies, all of that fun stuff when you get older. Okay, so if you were to look at the R value here, it's going to be very close to 0, right? But actually you have a curvilinear association, which means it starts as a negative association and ends as a positive association. It could also be the other around where it starts as a positive and ends as a negative. But this is something to look out for, and this is something that you can't see, again, with an R value. You would have to look at your scatter plots to detect curvilinear association. Okay. Internal validity, again, this is looking at causal criteria. It's not very important with association claims, but you still want to consider it because we want to make sure that we do indeed have an association claim. Okay, so the causal criteria we've already talked about. This should be a review. We have covariance, temporal precedence, and internal validity. Okay, so I'm going to show you this. Covariance is just showing that the two variables are correlated. So A and B are somehow associated, correlated. Association claims should have this. Temporal precedence is making sure one variable led to the other. If we can't tell A came before B, we cannot infer causation. And to have this, we often need to manipulate variables, which we can't do if we have an association claim and we're just measuring the variables. Okay, and then the third criteria is internal validity, also known as a third variable problem, which we'll talk about more in a second. So is A leading to B, or is there another variable, C, that is causing them both to change independently? Okay, if there's a possible, plausible third variable that we can't rule out, we cannot infer causation. Okay, and again, when we're manipulating variables, we're able to control, hopefully, for these third variables. Okay, when we're just measuring stuff, doing questionnaires, behavioral studies, or physiological, we can't necessarily control for other variables. Okay, so for example, the third variable problem, just to show you what I mean. So this is the well-being scale and the percentage of substantive conversations. Okay, so how happy people are and how much deep talk they have. What if these two aren't actually causing each other to change? Which, I mean, if we're doing an association, correlation, we're not necessarily stating that. But if someone wanted to say for a fact that one thing causes the other, our well-being causes us to have deeper conversations, or vice versa, a deeper conversation causes us better well-being. To do that, we need to rule out third variables, and one that we could easily think of is looking at more educated or less educated people. Okay, and this study was actually done. So these green dots are more educated individuals, the blue dots would be less educated individuals. And you can see that this correlation that we think we see is actually due to the education level. So more educated people are going to be having deeper conversations and are typically have better well-being than less educated people who typically have less deep talk and are not as well off. Okay, so we see an association here, but it's because of the education kind of separating these two groups. You see that? So this is called a spurious association. So it's still technically an association, an association that's happening because of a third variable, because of education in this case, but we still have a positive correlation between these two variables. but we cannot say that we have causation. Okay, one thing's not causing the other. They are correlated, but it's because of this third variable. Hopefully that makes sense to everyone. We could have something similar. Say our graph looks like this though. I don't know why they changed the colors, but this like orange one is more educated and the dark blue is less educated. If you saw a distribution of results like this, then this third variable is not necessarily causing the correlation that we see. So you can see here that within each subgroup of education, there's really no association, right? So we have a round circle. Would be probably a zero association within each group. Everyone see that? But the two groups together, there is a positive association. If you look at this graph over here, within each group, even the less educated group, although they're lower on the two scales, you still see a positive association within their data. And within the more educated people, you see a positive association in their data. Okay, so even though there's a third variable that is, more educated people typically are better off and have a better well-being, there still is an association even without looking at that variable. So you see how the ovals, these are ovals here instead of circles. So this is showing, that the third variable is not necessarily causing the relationship or the association in this case. Hopefully that makes sense. Yeah, and then the last part of this chapter is just looking at external validity. So looking at really how important external validity is, which might kind of surprise you, and then looking at something called moderating variables. Okay, so again, external validity is looking at how well the association can generalize to other people, other places, other times. The size of the sample doesn't necessarily matter as much as how well your participants were selected. Your sample is it representing your population well. Okay. So external validity, we've talked about it previously, but the sample you want to be as random as possible. But even if you can't get a random selection, you still might have good data, and your data could generalize to other populations as well. Okay, so just because you don't have a random sample doesn't mean you should automatically reject the association. Okay, so this graph is showing people percent time spent multitasking and multitasking test score. So we have old individuals and young individuals here. So say you were only able to get old people to participate in this, survey or whatever. So you only had the yellow dots here. Even though that's not really a random sample, it's not a good sample, it's not showing everyone in the population, it might still generalize to other populations. So we could look at what we do have, which is, old people, and your association between your amount of multitasking and how well you multitask. You would see a negative association. If you did the same study and were able to get young individuals, you would see that same association. So just because initially you didn't have everyone in your study, you can still generalize your results a lot of the time to other populations. Okay, so ultimately, you want to see if your association exists within different groups. Okay, so if you can't get your sample to be random and include everyone that you want initially, don't worry, it still might generalize to other populations. It's just something you have to kind of take into account, and as a researcher, balance, what's most important. And then the last bit here is talking about what's called moderating variables. And again, there's a YouTube video that explains this. It'll be linked on Educat. When a relationship between two variables changes depending on the level of another variable, that's considered a moderator. Okay, so again, there's a YouTube video. Please watch it. That explains it really well. It's a Khan Academy one. but the example your book gives, skip that. Your example your book gives of this is this moderating variable, right? So Arizona Diamondbacks in Phoenix. Phoenix is a town that has high residential mobility. This is a baseball team, right? So Phoenix, high residential mobility means a lot of people are moving in and out of the town compared to Pittsburgh, which is a low residential mobility town, whatever baseball team they have there. People in Pittsburgh don't move in and out very often. If you're in Pittsburgh, you're less likely to move in. There's less likely to be new people moving in, so on and so forth. Okay, so this study wanted to look at the correlation between game attendance and the percentage of wins. So in a town with high residential mobility, where people are moving in and out all the time, people are more likely to attend the games, so attendance increases as percentage of wins increases. Okay, so that's might be what you would call a bandwagon fan. If the team's winning, you have a town that people aren't really invested in the sport, but if the team's winning, people want to go to the games and attend those games. So you see a positive, stronger effect size with attendance and percentage of wins compared to Pittsburgh. Attendance and percentage of wins really doesn't have a correlation because those people who live in Pittsburgh are diehard fans, are going to go to the game regardless of how they're doing. Okay, so percentage of wins and attendance would be moderated by a third variable, another variable, which is residential mobility. Okay, if you look at this on a little chart here, Phoenix, the R value of game attendance and success be 0.29, and that's statistically significant. Pittsburgh, negative 0.16, and it's not statistically significant. Okay, so we do have a correlation that is statistically significant in Phoenix between, how many people attend the game and how well they do, but not in Pittsburgh. Okay, and it's moderated by the mobility of residents in that city. Okay, and again, please watch that video that I post to try to explain that better. All right, that's it for this chapter. Please let me know if you have any questions. Hope everyone's doing well. Miss you guys. Bye.